In this lecture, we're going to talk about real gas behavior. And we have been talking about gases and how they behave and what you would observe at room temperature or at 1 atmosphere pressure, similar to um, sea level. Uh, but gas behavior will start to deviate from ideal gas behavior in more extreme circumstances. And so we're going to take a look at that now. So, looking at real gases, they don't always behave like an ideal gas, and we typically see this happen at high pressures or low temperatures. Now, there's two assumptions in the ideal gas law as part of kinetic molecular theory that sort of break down under high pressure and low temperature. So the first is that we had to assume that there were no attractions between gas molecules. And it's okay to make the assumption that this is negligible because in our gases, the particles are so far apart. But under really high pressures or low temperatures, then those particles are going to come closer together. And so this won't be as negligible of an effect, and it'll start to have a meaningful impact on the gas's behavior. What we mean by attractions between gas molecules is that they're either attracted to each other or repelled by one another rather than just being near each other. And this is an effect of intermolecular forces, of the interactions of these balls of negative energy that have these positive centers with one another. And just Coulomb's law, like charges repelling one another and opposite charges attracting. Now, the other assumption from kinetic molecular theory that doesn't work in these really high pressures is that gas molecules do not take up space. Again, this is an assumption we made because these gas particles are so far apart. But when you bring them closer together, then it turns out that the volume of the particle becomes a meaningful percentage of the actual volume of the container. And we can't ignore it anymore. It's actually going to have an impact on the behavior or being able to predict the behavior. So these assumptions aren't valid at these at low temperatures or high pressures. Here's an example in the table or the chart on our page. And what we're looking at is pressure here on the bottom versus PV over RT. So what this really is here is it's really the number of moles, but it's looking at just this behavior of our gas. So if you're an ideal gas, then everything would be the same. Like you would predict the pressure would stay the same for any calculation that you were doing using just the ideal gas law. And what this is comparing is the pressure measured experimentally and what is predicted by the ideal gas law. And so what we're looking at is the deviation between what we see experimentally and what would be predicted by the ideal gas law. So if things behave like the ideal gas law, it would be that highlighted green line. And we don't see that. And we're looking at really, really different pressures than just right that what you're sitting in. We're looking at a scale of 0 to 1,000, which is huge. 1,000 atmospheres is an intense amount of pressure. And what we see is variation from ideal gas behavior. For molecules that are pretty inert, like helium and neon, and also small, we see that difference between ideal gas behavior increases linear with pressure. And we get these, so here's helium and here's neon. We get these kind of straightforward relationships. But we see these curves for things like water and xenon and a little bit argon. And what's happening there is we have larger molecules, or we have ones that are polar, like water, that are more polarizable in general. And so they're going to have stronger intermolecular forces between one another. And so they are going to deviate in a different pattern than something that is pretty inert and has few interactions. So let's study these one at a time. So here, let's look at the non-ideal behavior as an effective particle volume. So as we reduce the volume of a container, we increase its pressure. And so in our case right here, we have high pressure and low volume. And these particles are so close together and crammed into this space that the percentage of the space that's occupied by the particles itself within the volume becomes meaningful. This happens as pressure increases, as those particles come closer and closer together. And so we see these particles taking up space and that deviation from ideal gas law behavior happen um, at high pressures. And we see that the volume is always going to be larger than we would predict using the ideal gas law. So here's an example of argon and an ideal gas behavior for argon and the amount that they deviate as or as pressure increases down here. And this is all at 500 Kelvin. And so what we see is that at high pressures, our volume is always higher than we would expect, and that's because of the volume the particles take up within the space. So we can correct for that, right? So if we're seeing predictable behavior or consistent behavior based on our observations, we can try to build a way into our ideal gas law that would correct for this. And so what we're doing is we're starting off with just our ideal gas law that calculates volume, right? So we see volumes are larger, and based on the type of molecule it is, we can develop this van der Waals constant B that is going to be different for every gas particle because it's going to be dependent on the size of the gas particle. And it's going to correct for that volume. So what we're going to do is we're going to add that correction factor for each gas particle. So we're going to multiply it by the number of moles of particles we have. And this is our correction constant. And we call it a van der Waals constant. And it's B. And you would have to look that up. It's not something that you'll calculate. And it'll be different for every single thing. And so now we have an expression that will predict the volume more accurately for a gas that's at these kind of really high pressures by adding that correction factor. So the other real gas behavior that we have to account for is attractions and repulsions between particles. Essentially, forces of attraction or repulsion that are intermolecular, meaning between molecules. And so what we see is that they can attract or repel, and even really weak attractions will mean that the mean free path of our particles will be affected. They'll change. So an ideal gas will just shoot around, right, in random directions, always going straight. But if two particles come close to each other, like right here, we'll actually see them either repel or attract one another. And even though they're not going to collide and just come close to one another, they're going to change the path of each of their paths that they're on. And so it means that to go between container and container, the line isn't that particles traversing isn't exactly straight. But as it gets close to other particles, it's going to, because of attractions or repulsions, bend and move. And so our mean free path is longer than we would expect. That means that the number of collisions will go down as the mean free path increases. And what that really means is if it takes a longer distance for this particle to go from container to container wall, our pressure will decrease. So that means that we'll have a smaller pressure than we would expect for gases that are at really high pressures or low temperatures. And so we can take our ideal gas law solved for pressure and add a correction factor, just like we did to the volume. And what we're going to be adding is this factor right here, which is going to correct for these attractions and repulsions of our gas particles, creating a longer mean free path. So we're subtracting it because our pressure will be lower than we expect. So this factor is subtracted from just the ideal gas law. And we're going to use a new van der Waals constant called A. And again, this is going to be specific to every particle, like every molecule will have a different value of A. And that's because it's going to, um, be dependent on the chemical composition of it, and how its electron density is distributed through the molecule will affect how it would interact with other molecules of itself. And so we use that, and it will depend on the number of particles we have. So we include number of moles, and it will also be dependent on the volume, because that mean free path is dependent on the space that the particle has to traverse in order to go from one container wall to another to apply a force to it and create that pressure for the system. So now with these two correction factors, we can bring them together. And this is what we call the van der Waals equation, or the real gas law, instead of the ideal gas law. And so we have that correction for intermolecular forces and for the attractions and repulsions that happen that lengthen that mean free path right here. And we have our correction for our particles actually taking up volume right here. And to the table to the right, we have our van der Waals constant A and van der Waals constant B for a variety of molecules, from helium and a lot of other noble gases to some of our simple diatomic ones like hydrogen and nitrogen, to some that are common like water or carbon dioxide. And you can see we have a variety of different correction factors that go along with this. And so this is a correction to pressure and a correction to volume. And then our gas constant is the same, and temperature and moles are the same. Those aren't corrected for. And then this will allow us to predict a little bit more closely our different variables for gas behavior. And so what we see and what we should expect when we're thinking about real versus ideal gas behavior is that PV over nRT ratio for a real gas, which is really what we'll do is call this is like our calculated behavior, is generally going to be lower than ideal at lower pressures. And so here are our lower pressures. And by lower pressure, I'm going to put that in quotations because 200 atmospheres is not low. But compared to 1,000 atmospheres, it is. But when we're down kind of in this region here away from 1, we see that a lot of these gases are actually going to be predicted to have constants that are lower than they would be at higher temperatures. See, they get really high up here on this end. And that's really because at lower pressures, between these two correction factors, the one that's more meaningful is the one that corrects for intermolecular forces. So that's going to be the stronger deviation from ideal behavior at lower pressures. It's how those particles are attracted to one another and the change to the mean free path. But at the really high pressures that we have, then the most influential factor is going to be the molecular volume. So the higher that pressure gets, the more meaningful the volume of a molecule will be relative to the volume of space that the gas is occupying. So in general, lower high pressures, we have intermolecular forces play a larger role influencing the predicted behavior of a gas. And at high temperatures, the volume of a molecule will have a larger influence over the behavior and how it deviates from ideal behavior for that gas.